Okay, let's get started. So, if you haven't picked up your midterm one, they're up here. If you gave it to me for regrades yesterday and I haven't given it back to you yet, those are up there too. Homework ones are up here that are for people who haven't picked them up yet either. I don't have homework twos yet, so I'm probably going to get homework twos next week, and then you'll get them then. Are there any questions? Yeah. Other questions? Okay, so what were we talking about last time?
PDAs.
Yeah.
CFG to PDAs.
Yeah, so we were doing this conversion from a CFG to a PDA. So what is a CFG?
Context-free grammar.
A context-free grammar, and then a PDA is a what? Yeah, the push-down automaton. So to get the idea, what we built was a machine that had a state, and then we pushed on the dollar sign or a special character. It doesn't really matter what it is. Then we pushed the start symbol on. Then what we did is we had two types of transitions. We had ones that just did a simple self loop where we read and pop same character. And then we had longer transitions that what these do is pop off variable, push on right-hand side of the rule. Because if we saw a variable, since we're doing the derivation on the stack, we put the right-hand side of the rule on. And then at the very end, we pop off the dollar sign, the same special character to go to a final state and accept. So therefore, PDAs recognize the context-free languages. Is that correct? We have to show the other way. Well, this shows that any context-free language is recognized by a PDA. That's true because of this conversion. But it could be possible that a PDA is more powerful than a CFG and can get any non-context-free language if there are any. So we need to be able to show the other direction. And what were the things that we talked about last time to get started? So what did we first do to the PDA to make it a little easier to work with? There was some simplification we did to the PDA to make it a little easier. Something to do with the final states. Yeah, so we made sure that the PDA has exactly one final state. And then once we did that, we looked at the reasoning behind that because since this new final state has no transitions coming out of it, so all of these are epsilon transitions. So I'm lying a little bit, but there are epsilon transitions that go to this new final state, and there's nothing leaving that final state. So if we look at what the strings that are accepted do, they start in the start state and go to the final state because there's only one of them. So what we thought of is, well, if we want a CFG for this arbitrary PDA, what we need is for the CFG start variable, whatever that is, to represent all the strings that take us from the start state to that single final state. If we had multiple final states, that wouldn't work because some strings might go to this final state and other ones can go to this other one. So by putting a single final state here, we have exactly one place to go from the start state to the end state, to this final state. So we're going to make a start variable that encodes that. So we're going to make a start variable that encodes all strings going from start state of the PDA to the single final state. If we had multiple, this wouldn't work because we can't have multiple start variables. Okay, great. So if we make a variable that does that, we're good. But the problem is all PDAs, a lot of PDAs have at least two states. So it's not the simple case where we just have a single start state that goes over to a single final state. We have usually something a lot more complicated. So if what we noted last time is if we have the start state over here, the final state over here, and if we did a lot of transitions to go to some state in the middle, and then some other states to go over to the, some transitions to go over to the single final state. Well, if I know how to generate the strings in the first half, and I know how to generate the strings in the second half, we noted that it's just concatenation of the strings we can get from the first half and the things we can get from the second half. Seem reasonable? There's a little bit of a problem though, as there always is. Is there something temporal, time-related with PDAs? So I'll give you more of a hint. If we visit a state and then we come back to it at some later point, could the stack contents change? Have changed when I revisit it? Yeah, it definitely could. So what could happen is we could have a set of transitions that come back to the same state, but the very next transition I take is different because the stack contents are different, possibly. So we need to be able to say, well, if we go from this start state to this middle state with the same contents of the stack at each point, and then from the state in the middle to the final state with the same contents of stack, then everything carries through. Because if we have the same stack contents, we'll do the right thing anyway. We'll make the right choice to go to the final state because it's non-deterministic. So we need variables that encode going from one state to another and with the same stack contents at both places, at both states, I guess. So, well, that would seem reasonable. If we can go from one state to the other with the same stack contents at both places, then we can actually get somewhere. Well, here's the thing. What does this, when we enter the start state, turn on the PDA right at the start, what is the stack contents at that point? Empty. So that must mean, for that reason, we need to be able to go to the final state and have no stack contents left. We need to be able to empty the stack in that final state. But do PDAs have to end with an empty stack? No, the only thing that matters is reading the input. So we can't actually force the stack to be empty. Well, what you can say, well, why don't we just have a bunch of transitions that just pop all the symbols off the stack? Well, the key there is if we're just popping things off the stack and in that final state, we can't read anything because we should be in a final state and never have to read anything else. So we can't read anything. but that means we don't have to execute the transition. So what we're going to do is we will allow, so not force, the stack to be emptied in the final state. And a very simple way to do that is we have all the transitions coming into that single final state. So if you recall, these are all triple epsilon transitions because we don't want to do anything going to the final state. And then what we're going to do is we're going to add a self loop on that final state, which is just we're going to pop each character from the stack alphabet. So for each symbol A in the stack alphabet, we're going to put a self loop on there saying, don't read anything, just pop that symbol and don't push anything. So remember, these transitions are not required because we're in the final state already and we've read the entire input supposedly. So there's no issue putting these here because I'm not going to change the language, but I'm allowing the stack to become empty. Okay, does that sound fair? Any questions? Yeah, go ahead.
So even if it's not empty, though, it can be accepted. Because it goes at the final state, and then it goes.
Yeah, so if it's not empty, because we don't have to have the stack be empty to accept, we can still accept before. It's just I'm allowing you to empty the stack if you want to. Or partially empty it, I guess.
So in test, you have to set empty.
Do you have to what?
Or like if empty, like you have to empty it at the end.
You have to allow it to be emptied, yes. Mm-hmm. Because there's a reason for that, and we're going to get into that. Other questions? Well, here's another issue. Well, suppose that we are in a particular state and we have certain stack contents, come back to it, we want to have the same contents of the stack. But the issue is, what if we come back and the same stack height is there, but a different symbol is present on the top? Then we may do a different transition. So we really want the stack to be have the same contents, but it's actually a little difficult if we allow you to simultaneously pop and push on a single transition. So what we're going to do is we're going to simplify the PDA even more. So, and we'll see why we're doing that. So what we're going to do as the final simplification, we're going to ensure each transition either pops or pushes, but not both. So every single transition is going to do something to the stack. So we're going to either push something onto the stack or we're going to pop something off. We're not going to do both operations at the same time, and we're not going to do neither operation. So every transition modifies the stack in some way. Yeah. Okay. Any questions about that? Well, can I actually do this? Can I do this with an arbitrary PDA? Well, if we have a transition that just pushes and doesn't pop, do we need to modify that? No, that's fine. If it pops but doesn't push, I think that's okay too. But if it does both, we definitely need to do something about that. So let's just say we have a transition like we read an A, pop an X, and push a Y. So that could be a transition that happens. Well, could I simulate this transition here with maybe more transitions that do exactly one of the two operations each. So what do I do? What could be a solution to that?
Pop X, then push Y.
Yeah, so pop X and push Y. So that's actually the correct way. Here's an incorrect way, and I want you to tell me why. We're going to push Y first and then pop X. Yeah, if we push something on top, the thing we want to pop is not there anymore. So we got to pop first. So what we're going to do is we're going to put a state in the middle. And we're going to fix this with two transitions. So this red state is a completely new state. It's never been seen before. And what we're going to do is we're going to pop on that transition and don't push. And on the second transition, we're going to not pop and then push. It doesn't actually matter which transition actually reads. I like putting the read transition on the first one and no read on the second, but it doesn't actually matter here. As long as we're doing the pop first and then doing the push, okay? Well, what other kind of a bad transition might occur? Yeah, I don't do either. So we may have a situation where we read an A, don't pop and don't push. So what would we do in this case? Yeah, push something and then pop. That's the correct answer. Here's an incorrect answer. Pop whatever's on top of the stack and then push it back on. What's wrong with that idea? What's that? Well, I'm pushing it back on. That's the thing. Well, what I could do is I could have a bunch of transitions that correspond to, well, you could have popped this thing or popped this thing, or actually that. Yeah, so here's what you could do. So this is, don't do this, but don't do this at home, kids. So what you can do is you can have a bunch of transitions going out to a bunch of new states for each of the characters. So for each stack character, you can have its own separate path, and then you can push it back on going to the other state. So there is a way to actually get around it, but it's more complicated than necessary. But the issue is that we're popping first, and what could be the issue? The stack could be empty. So if we push something, there's never an issue with that. So let's instead push some arbitrary symbol and then pop that same symbol back off. So let's put our red state in again. Then let's read on the first one again. Don't pop, and then let's just push some symbol X. It doesn't matter what it is, because we're just going to pop it off anyway. And then we're going to pop the X, the same symbol back off, and then don't push. Well, that's actually pretty easy. Yeah, go ahead. Oh, thanks. I get carried away sometimes. All the time. But in fact, no matter what transitions we have, we can transform the PDA into this form, where each transition does exactly one of the two operations. So you may think, okay, why the hell are we actually doing this, right? Why are we making this simplification? So the reason for it is something that, so in this area, theoretical computer science, you sometimes see these results that are basically just out of pure brilliance or just pure magic. And this is actually probably the only one that we'll see in this class. I don't even understand how they came up with this idea, but it actually works. Sometimes if you just try various things, it'll actually work. And in fact, some of the research things that I do, one of the most important results that I've proved was from trying something different. Okay, so what the people did, whoever authored this paper or wherever it came from, was to look at this. So we're going to make a simple graph here where the horizontal axis is time, and by time I mean the number of transitions that are taken. So at the beginning is right when we turn on the PDA, and then we're just going to look at what happens as we take more and more transitions. And the vertical axis is the corresponding stack height. Okay, so we're just going to look at a simple graph over time through some computation of this PDA, what happens to the stack, okay? Well, at the very beginning, what happens? What is the stack height at the very beginning? Yeah, nothing. So at the very beginning is down here. What is it allowed to end as? Also 0. Cool. Could the stack height in one transition stay at 0? No. Why not? What did we do to the stack on every transition? It has to change no matter what. It can't stay the same height before and after because we eliminated both of those occurrences. So no matter what, the stack height must change. So for that reason, what happens to the stack on the very first transition, assuming the PDA is okay? It has to go up, right? So the very first transition has to go up. Could the second transition go back down? Yeah, it is possible. So, but the second transition could also go up. It can't stay flat for sure, but it can go up or down. So what you may notice is that you can have stack heights that are like these mountains. Fire mountains. So, yeah, they really do like fire. But, yeah, so it could look something like this. It's never flat. That's the key here. Okay? Well, let's see. Let's actually take a close-up look at this part right here. So I'm going to make it a little bigger. So let's just say that this is the very first transition. And here's the next transition. Sorry, the next state that we're at. So this is one transition pushing up. And then we do the middle computation, which is this mountain thing in the middle. And then at some point, because we end with an empty stack, or are allowed to at least, at some point we come back down to 0, come back down to Earth. So at some point, the stack height became 1 again. And then at some point, maybe in the circle part or at the very end, it came back down to 0. I'm not saying it touches down to 0 in the middle. It might not. It may do it many times. I'm just saying at some point it comes back down to 0. And let's just say in the dotted part right here, it never touches 0 at any point in the dotted part. What can you tell me about these two transitions? The one where it comes up and then it comes back down.
Pushing and popping the same thing.
Pushing and popping the same thing. Because it never came back down to 0, so it couldn't have changed that character. Yeah. Oh yeah, okay. Anyone have a question about that? So if you never come back down to 0 because it's a stack, whenever you have a situation like this, where you have these matching transitions, then it must be the same character, where you push some character and it pops the same character at the end. That's pretty interesting. Well, here's something else interesting. Look back at the figure we had before of the stack height graph. So let's just say that the variable that generates this part is A, and then the variable that generates this part is B. Can you tell me how to generate the strings that take me from the beginning to the very end? If you know how to do the first part and the second part, how would you do the combined part? Well, it's anything that the first part generated, any part read on the first part, and then anything read on the second part concatenated together. So if we want the whole thing, then that would correspond to looking at the rule where you replace some variable with a b if you want to get both parts. Okay? Let's see. Well, so if we know how to actually do this part right here, where you have these matching transitions, then you can just work your way one further in on both sides. Well, at some point, you're just going to keep building up higher and higher until you reach some peak somewhere. Okay? At some point, you're going to be at the very top of these mountains. Okay? Along the way, we know how to actually do that because they're matching transitions. But at the very peak, we may not know what to do. Well, let's look at a peak. So here's a peak right here. So these two transitions are matching because they're the same stack height. But at the very top, we need to be able to resolve this base case of sorts. So we know how to deal with this inductive case, handling these matching transitions and working your way in. But the base case, when you're at a single node, we need to figure out. Well, let's see. Well, that corresponds to, well, if I'm going from a state Q right here, going to state Q prime, which is my target, and this intermediary state Q double prime. Well, if I know how to get from Q to Q double prime, and from Q double prime to Q prime, that's just the inductive case before. So what we need to know is, how do we get from Q double prime to itself? Okay, because that's the base case. If I know how to work your way up, the base case is, how do I get from the same state to itself? Well, there are many ways that could happen, right? If I'm in a state, there are many possible ways that I could go back to that same state. But what is one way we can do that? What is one string that we can read that goes from the same state and doesn't do any transition? Empty string. So we'll have a rule that corresponds to going from each state to itself and generating no string, generating the empty string. Okay? Cool. So just as a high-level idea, what we're doing is we're looking at how to get from one state to another and making a bunch of sub-problems, little tiny problems, and then combining the sub-problems together to get the one that we want at the very end. So we're going to make a bunch of variables. So we're going to make a variable of the form a sub q prime for all pairs q and q prime as states. So, yeah, go ahead.
Sorry, I heard you were going to say this, but Q and Q prime mean that they have the same number of elements in the stack?
Yeah, so this variable, a sub something, that's what we want it to mean. I'm just making a variable now, but that's what we're going to make it become. Other questions? Okay, cool. So I think this base case is pretty easy. Going from the same state to itself. Well, could that scenario happen at any state at all? Yeah. So what type of rules do you think we're going to put in? Well, sorry, I should say, which of the variables are we going to use? Well, the variable represents going from Q to Q prime with the same stack content, blah, blah, blah. So if we're going from the same state to itself, and it can happen for any state at all, what type of variables are we going to use? A sub what? Well, should it be the same state in both of the subscripts here? If we're going from Q to Q prime, if it's going from the state to itself, it better be the same state. So we're going to have the rules of the form a sub q q Yeah, so I'm going to stick to this notation. The CSE notation is slightly different. I think they use A sub P, P or something. I'm going to use Q because I'm a rebel. What's that? Yeah, so Q. So this is for each single state in Q. So this rule right here doesn't relate any of the states to any other state. It's just each individual state by itself. So if we had the start state Q0, we would have A sub Q0 generates the empty string. And we'll do examples of this. Okay, so there are actually 3 types of rules, and this is the first type. So this is what we call type 1 rules. So type 1 is just this single type of rule, where we have A sub some state, but then the second one is the same state as the first one. It generates the empty string. Any questions about that one? Because this is the easiest one of the 3. Any questions? Okay. Well, it seems like if we can get the each individual mountain okay, then I think everything else falls through once we get the transition one. So if we can handle the simplest case, let's handle the most general case and then work on the middle case later on. So for this outer case right here, so what could happen is at some point it may not be the beginning or near the end, it could be in the middle. Let's just say we were in some state Q, and then the destination over here is Q prime. We're still eyeing our target on Q prime. But let's just say there's some middle state in our way, Q double prime. Evil Q double prime in our way. Let's just say that what happens is we're at some stack height at Q, and Q prime's at the same stack height. So what could happen is we have these mountains in the way that we need to traverse. And then let's say that Q double prime is at the same stack height as the other 2. Well, let's say that is the case. Well, what is the variable that takes me from Q to Q double prime? Just translating it in. A sub Q, Q double prime. Just translating the notation over. So assuming we can do a single mountain, that's our assumption right here with this variable. What about the second half? What variable corresponds to that? A Q double prime. So the double prime, so the first one of the second variable matches the second one of the first variable. But the ones on the ends could be arbitrary. So as long as the middle 2 indices match, then we're okay. Well, so what type of rule should we put here? So what is my start and what is my destination? A Q to Q prime. So I want to go from Q to Q prime. What could I replace that with in terms of what we just did?
A Q double prime.
Yeah, so the first, reading something from the first one, and then concatenating it with something from the second variable. So A Q double prime, Q prime. So think of these like subproblems. We have these 2 subproblems, and we're combining it to a larger one. So assuming we know how to do the smaller ones, then we know how to do the larger one. Okay? Any questions about that? So the first type of rule was type 1. What do you think this type is? Type 2. So this is type 2. But here's the thing. Could this happen for any Q, Q prime, and Q double prime? It could. Well, we may be able to exclude some triplets of states if it turns out to not be necessary, and we'll see an example of that. But if we actually put in useless rules, ones that won't do anything, does that help? Does that hurt us? Well, if we have a rule that's just completely unnecessary, there's no harm in putting it in. So we might as well just do this for all triplets, and by that I mean just 3 sets of states. So Q prime, Q double prime as states. So for all triplets of states, just make this rule. So one other thing you should note. For type 1 and type 2, did we even look at the PDA's transitions at all? No, we didn't even care what the PDA actually did. All we just did was make these rules for each of the states or each of the triplets of states. So for type 3 then, we're going to actually look at the transitions. So the only cases that we need to settle right here are the matching transitions. So what are the matching transitions? So we have something like this. So just like before, since we're dealing with a single mountain right here, we're never touching back down at 0 at any point in the middle other than at the very ends. So we know that they end up at the same stack height. So let's see. So the first transition, let's just say pushes an X. Well, what does the second transition have to pop? It has to pop X because it never touched 0 at any point in the middle. So pops X. Well, it could be that these 2 transitions read or don't read or read different things. Let's just assume that the first one reads an A and the second one reads a B. The A and the B in both of these cases could be both epsilon. I'm not supposing that they're input characters or whatever. I'm just handling this in the general case. Well, let's see. Q is our start, Q prime is our target, and let's just say that the states in the middle are R and S. It could be that all 4 of these states are exactly the same, or they could all be different, or some different combination. Let's just assume that they're different for generality. Well, let's see. What are we assuming that we can generate a string from? What state to what state do we assume we know how to do? Well, we know how to go from Q to R because it's the read A push X transition, and the S to Q prime one, we read a B and pop X. Because we know what we read on those transitions. What do we assume by induction that we can do? Well, Q is our start and Q prime is our target. What is another pair that we're going to assume by induction we know how to do? R to S. So why R to S? Well, think about what the mountain looks like. It's at some level right here, and we're going in one level, and then at some point we're going to go in another level, until we reach the top, which is settled by the type 1 rules. So we're assuming we know how to generate the R to S. So how do I get a string from R to S? By induction. What variable gets us there? ARS. Yep. So ARS, that's the variable we are assuming can get us from R to S. Okay? We'll generate some string. Well, how do I then go from Q to Q prime? Well, what string will, as an example, would take me from Q to Q prime? Well, I gotta follow the read transition first. So what thing do I read on that push transition? Just a A, yes. So I will generate an A right here. Then what string are we assuming we know how to generate? something from ARS. So we're going to defer the work over to that other variable and let it do its thing. But remember, our target is Q. So what else do I need to read to, Q prime. So what else do I need to read to go to Q prime? Read a B. So after I generate the thing from R to S, I need to read a B. But that will take me from Q to Q prime. So why would this work? Because we have all these mountains in our computation, a sentence you probably will never hear again. We have all these mountains in our computation, haha. Well, if we subdivide them, if they touch down at 0, well, type 2 will fix that for us because we can just focus on each individual mountain then. If we have 2, then we can just forward the work onto each one of them and concatenate the result. If we have a single one to deal with, we have a matching push and pop, but then, so that's a type 3 rule, and then we can just inductively work our way up until we reach the peak at some point, but then that is settled by the type 1 rule. So in fact, this gets us exactly what we want.
What about push X and pop? Where does it occur in the graph?
So because we had the PDA can't do both operations on the same transition, that'll never occur. So the transitions will always make the stack height go up by 1 or down by 1. It's never flat, which is allowing us to match these transitions together. So as long as we have 2 matching transitions, we're okay. I can't match a transition that pushes an X and pops a different character like Y, because they can't possibly correspond to matching transitions. Okay? So as long as I have the same push and pop, they could be matched. Well, could this happen for any push transition and any pop transition? Yeah. So even if it makes absolutely no sense, as we'll see, we're going to put these useless rules in anyway. So there are productive ones that will work, but some of them won't work. We might as well just put them in anyway because it doesn't harm anything. So I'm just going to say we're going to do this for all matching. I'm not going to get into the formalism here. For all matching transitions. Whatever that actually means. Okay? I think it's actually a good time for a break, and then after the break, let's do an example.